Warm-up questions for day 125, convex mirror introduction. Warm-ups, law of reflection. Try to write that down. We went over it yesterday. Do you remember? I'll give you a hint. It starts off with theta sub I. Does that help out?
Theta sub I equals theta I, or theta, whatever.
Theta sub I equals theta sub R. The incoming angle equals the reflecting angle. Remember that these are the angles relative to the normal, not the surface. So if this is the mirror, this is the normal, 90 degrees to that surface, and when a ray hits here, we're talking about this angle here as the incoming, the incident ray. And then the reflected ray, the second ray, is that angle there. Convex mirrors, these are like on the outside of a bowl. Yesterday we were looking at concave mirrors, the inside of a bowl. Does anybody know when they've seen the convex, the outside of a bowl? I don't know of any time where we purposely use them, but you can see them nonetheless with spoons. There have been many a day where I've been very, very bored as a young person, elementary, junior high, or at a restaurant or some other kind of a gathering. You're just so bored waiting to get excused from the table or whatever, and I'd look at these reflections in the spoons. Okay, last class we did a lab where we determined the focal length of concave mirrors. You should have reported your answers onto Schoology, and you had a few other questions on that. Does anybody have any concerns about that assignment? Today's purpose is to learn how waves behave when they strike a curved surface of a material on the outside of a bowl, called convex. We do see these in stores, parking lots, side view mirrors. Success, you can draw a ray diagram for these things. Okay, once again, just to review, convex is when the middle bows out towards us. Concave is when the mirror middle bows away from us. So how do you draw a ray diagram to find the image in a convex mirror? How can you deduce the new rules? Where's my ruler? Here's a ruler. What do you think is going to happen when a parallel ray that's parallel to the axis, hits the surface there? Now this is a solid mirror. It is not a lens where the light passes through it. This is a reflecting surface. Imagine a concrete surface like this, and you're throwing a ball, a bouncy ball, basketball, racquetball, tennis ball. How would you describe a rule that says how this bounces? Chris? It's going to go up higher, yes. At what angle do you think? How would you describe the angle? Think about how we did the rays for the concave mirrors. How would you describe this? Yeah? Okay. When we had our concave mirrors, a ray that went parallel went through the focal point. This is still going to have a connection to the focal point. We're going to say that it reflects as if it came from the focal point, from the direction of the focal point. Lines parallel to the mirror are reflected away from the focal point. Once you draw the reflected rays, cross off the incoming rays. In order to figure out where the image is, we only use the reflected rays. Okay, now, in our previous lessons, when we had the concave mirror, we would then draw a line that goes through the focal point. Remember how that reflects off of this concave in the past? Wade, how did this reflect?
I don't recall.
It reflected parallel to the axis. So, in this case here, when we have a ray that's going towards the focal point, it can't get to the focal point because the mirror's in the way. Gosh darn it. It's a solid mirror, so it cannot go through the mirror to the focal point, but how do you think this is going to bounce? Chris? Oh, I'm sorry, I meant Christian. That's all right. Yes, it's going to be at a lower elevation. Christian, can you describe how this is going to reflect, do you think? Okay, there's a same kind of a connection between focal points and parallelness as before. When one's going towards a focal point, it's going to get reflected parallel to the axis. If you look at the normal at that point, it's going to reflect in that way. So things that start off parallel end up coming from the focal point. Things that go towards the focal point end up going parallel. Once you draw that reflected ray, crisscross, scribble out the incoming rays. Okay, now, we have two reflected rays. If I was sitting out here, where would these two rays appear to have originated from? Well, they don't crisscross. But if I extend the lines, this ray appears to have come from somewhere back here. This ray here appears to have come from somewhere back along this line. So where those apparent paths crisscross, that is the image. The crisscross is above the principal axis, and so the image of the point is above. Remember, the base is always on the axis itself. So the point is up here, the base is down there, the image is right side up. It is reduced or shrunk. It is smaller than the actual object. Light rays do not actually travel behind the mirror. The mirror is solid with silver paint on it. Light cannot get through it. It just appears like it came from that spot. So we call that virtual. I didn't fill out this blank, did I? Lines that head towards the focal point end up reflecting parallel. Okay, so as we get closer to the mirror, the object was way over here, now it's here. How do you think that this image is going to change? Will its position change at all, or will it stay in the same spot? Will the size change, or will it stay the same size? Will it be flipped, or will it be right side up? So think to yourself. The first line we're going to draw is this parallel ray. How is that going to appear down here? Will the angles change? Will the lengths change? Will the position that this red parallel line hit the mirror, will that position change at all? Now think about this slanted blue line. As I draw that here, how is it going to appear? Will it change at all? Will it change in its length? Will it change in the angle? Will it change in the position hitting the mirror? Think about tracing those lines back. Where will the crisscross be? Okay, let's see how that went. The first line, the parallel ray, is still going to be parallel. it's just going to be shorter until it hits the mirror, but it's going to hit the mirror in the same position as up here, because it's parallel, same object. It's going to bounce up at the exact same angle. Since we're leaving the mirror at the same position, we're drawing this angle from the same spot, the F's. Everything is the same about the red. Once I draw the reflected ray, I cross off the incoming ray. The slanted ray, going down to the focal point, this one is going to be steeper than before. You are closer to the F, and so the line down to the F is going to be steeper. It's going to hit the mirror at a slightly higher place and then bounce parallel. This distance here is higher than this distance here. So when I extend this backwards, the crisscross place is going to be higher up than in the previous example. And so the image is going to be a little bit bigger. Not only that, but notice it's a little bit closer to the mirror. It is still right side up. It is still reduced compared to the real object. It is still virtual. These images are called virtual because we just have to imagine that light rays were traveling back there. These virtual are always behind the mirror. If you have an image in front of the mirror, it's always going to be a real image that you can project onto a real projector screen. This kind of image is always right side up. It is always above the axis. Real images are always upside down. Real images are always below the axis. Why do some stores have round mirrors in the corners of the room? Okay, so let's say this is a store. Here is the cashier's place. Here's the happy cashier. And here are all the shelves. We're looking at a bird's eye view of the store. So people walk in and they go, but this happy cashier cannot keep track of all these bad guys who are out to shoplift. Once again, this is a bird's eye view of the store. The shelves are kind of in the way. And so you might have seen these curved mirrors in the corner. Not that big, of course, but just giving you the idea. That is better than having a flat mirror. If I was to have a flat mirror, then the happy cashier can look in the mirror, but they only see this portion of the store. Looking at the equal angles, with a flat mirror, you'd only see one section. However, with this, we see more angles. This, we'd only see one small section because we have one normal. The normal is going in this one angle. But here we have a normal at this angle. Here we have a normal at this angle. Here we have a different normal at a different angle, and so on. And so to see that guy, I can look at this part of the mirror. Here I have a different normal, so I can see a different portion of the store. And here I have yet another normal, so I see a different part of the store. So why do some stores have round mirrors? Gives a wider range of view. Why do the car mirrors have the words "objects are closer than they appear" written on them? Again, we have a curved mirror because that allows us to have a wider range of view. We see not just the one car that's on the side of us, but we can see all sorts of cars in different positions. You have a smaller blind spot. But since it's curved to give a wider range of view, it makes the images reduced. Remember back here, all of these images were smaller than the actual object, and our brain perceives smaller things as being farther away. So side mirrors are convex mirrors. This is so you can see a wider range. These make all images reduced, so our brain perceives them as being farther away. Funhouse mirrors. They're wiggly woggly if you look at them in profile. Some parts are convex, some parts, and those parts make the image smaller and upright. Some parts are very concave. That makes you smaller and upside down. And some parts are slightly concave. Remember, concaves can make either a real image that's upside down, reduced, or, if you're in the right position, the right curvature, they make right side up magnified images. So here, when we have the wiggle and woggle, this section here is convex, this section is concave, this is convex, this is concave. So you have different kinds of images made in different parts of the mirror, and so when you look at your image, some of it's upside down, some of it's expanded, some of it's shrunk, and it makes it all crazy. I have a funhouse mirror in the back. I'll get it for you guys in just a second. Remember, all virtual images, virtual, are behind the mirror. All of them are above the axis. All of them are right side up. That's virtual images with the dotted lines. Light rays don't really travel there. All real images are in front of the mirror. All of them are below the axis. All of them are upside down.